inviting me to this meeting. So let me introduce myself. I'm Daniel Barci from State University of Rio de Janeiro. Here is my place. This building is our university that you see that it's very, very near Maracanã Stadium. And if you, few minutes to the south, you reach this beautiful place. This is Ipanema Beach. And so you can decide where you prefer to work. And if anyone wants to visit that, so you are very welcome. And okay, let me okay. It's not working this way. Yeah, let me. Full screen, right? Full screen mode. Okay. Which is the you know to pass? Oh, this one. Next here. Okay. Okay. Right. Okay. Let me present my collaborators in this work. Miguel Moreno is from Peru. Is my PhD student. Xochitl Gonzalez from the Mathematical Institute of the same university, and Daniel Stariolo from Federal Fluminense that should be here, and Lucas Nicolau that is around. Okay, let me talk about the motivations of this work. I mean, fortunately, I don't need to convince you that to study out of equilibrium statistical mechanics is an interesting thing. And in this talk, I will focus in non-equilibrium stationary states. I mean, states where the observables are time independent. However, you have currents, no detailed balance, no time reversal, etc. And the point is, if it is possible to write or to build some type of potential to describe this this non-equilibrium state in order to study, for instance, phase transition. And I mean, there are several approaches to study out of equilibrium statistical mechanics. One of these approaches is the stochastic approach. This is the approach that I will talk about. So the point is that when you have a stochastic process, how do you define equilibrium? And it's essentially when you have zero current probability. And when you have a stationary state out of equilibrium, generally you have currents, no detailed balance, microscopic irreversibility, entropy production in general. And the point is, how do you reach with a stochastic process, this type of a state? And you need essentially two ingredients, that is nonlinearity and noise. And when you mix these two ingredients, you have several interesting phenomena. One of them is stochastic resonance, and the other one is noise-induced phase transitions. We are working in both of them. However, I decided to talk about, in this talk, the second one. And so what it is a noise-induced phase transition is, imagine a system that for very low noise, or even for no noise at all, I mean, the deterministic system is in a disorder phase. I mean, you have essentially a potential that have a single minimum at zero. I mean, this is essentially disorder phase. And when you put noise in the system, and when you increase the noise, the system order. I mean, you get order from disorder, essentially. And this is what we call a noise-induced phase transition. And okay, so these are just some reference to show you that this phenomenon is observed in several areas, essentially in biological system, neural networks, chemical reactions, so that. But here, I'm not interested in any type of applications. What I'm trying to understand is, which is the physics of the noise-induced phase transition and the mathematical structure behind this transition. So the first ingredient that I need is multiplicative noise in order to reach this type of non-equilibrium state. And essentially, multiplicative noise is when the fluctuations depends on the state of the system. And some examples is in homogeneous diffusion. Typical example is a Brownian motion near a wall. So the diffusion constant is not a constant. I mean, it's a function of the of the distance to the wall. We have several papers in this area. Other example is micromagnetic dynamics, when you essentially, when the spins in the ferromagnets couple a fluctuating magnetic field in a multiplicative way. But okay, these are just examples. And let me define more precisely what does it mean, multiplicative noise. So we are talking about a system of Langevin dynamics that are characterized by essentially by the drift force and a diffusion matrix. You see that the noisy part of the Langevin equation is essentially a multiplication of a white noise times certain function of x, and this is why we call multiplicative noise. If this function is a constant, so we are in the usual Langevin additive noise. Okay, you see that, I mean, in order to define this equation, we need to correctly define this product. I mean, this is the way physicists write differential equations. However, mathematics never do that, just because this product is not well defined. Just because if you try to integrate this equation, you need to integrate a Wiener process. A Wiener process is not integral. It's not integrable in the sense of, in the Riemann sense. So you need to define this integral. I won't enter in details of that, but essentially we use a continuous parameter that I'm calling alpha between 0 and 1. That means that for each value of alpha, the integral is defined in a different way. So for each value of alpha, you have a different stochastic process. And special values of this alpha are very famous and has names like, for instance, alpha equals 0 is the Ito prescription, alpha 1/2 is the Stratonovich one. And I mean, you can have a lot of prescription, or stochastic prescription, in order to define this product properly. But, you know, this is technical. I won't enter in details. Let me show you, I mean, how we deal with this type of system of equation. The first, I mean, you have different schemes. The first one is Langevin equations. I mean, try to solve these equations. Of course, you cannot. So essentially, you do simulations with the system. We are doing that. Other formalism is the Fokker-Planck equation. And for this equation, you have some approximation approaches like mean field, perturbation theory, even some kind of normalization group that you can build up. And the last one is path integral formalism. That is the formalism that you will use, and is very appealing when you try to understand symmetries, potential, and you can use the power of non-perturbative quantum field theory in order to make computations. So let me say a few words about the path integral formalism. This is not new. I mean, this is a lot of people is working from the 70s, essentially Martin Sicha-Rose, Janssen, De Dominicis, Doi, Langouche, Tirapegui, Pellitti. I'm sure I am forgetting somebody, but anyway. the idea is that you can compute any stochastic correlation function just computing derivatives of some functional that is defined in this way. I mean, a stochastic average of an exponential of j times x bar. X bar is the solution of the differential equations. And the funny thing is that you can represent this functional in terms of path integrals without solving explicitly the Langevin equations. And I mean, we make some contributions recently to this formalism, especially related with how to deal with multiplicative noise, and especially how to implement this stochastic calculus inside the path integral. But anyway, the point is that you can write this functional very similar to a partition function. I mean, you have a path integral. This is essentially a measure that resembles a curve space, essentially, because this j that comes from multiplicative noise is like the same thing of curve your space. And you have an action, essentially, that is written in terms of the drift force and the diffusion matrix. But the funny thing is that when you have this representation, you can define dynamical potentials in a way very, very similar that you do in equilibrium. Essentially, you can define that f that is, let's work in that, okay, here, that f that is a functional to generate connected green functions, and you can define a local order parameter just computing the first derivative. And if you can invert this equation, I mean, write j as a function of the order parameter, you can do a Legendre transformation and compute a functional that is a functional of the order parameter. I mean, this is formal, but the difficult thing is that then you need to take the thermodynamic limit. I mean, the width of the system needs to go to infinity, and you need to keep constant some densities, and after that, you need to take time going to infinity, and if the system reaches some stationary state, you can define a potential that is essentially the same thing as the Gibbs free energy, but not for equilibrium. I mean, for a system that is out of equilibrium. Yeah, it's important. Yeah, because the dynamics is important. I mean, if you have a finite system and go the time to infinity, it's not the same that you have an infinite system and see how it relaxes. Perhaps, I mean, if you do this limit first, you don't know really if you are equilibrating the system in some. Well, it depends on the system. I mean, if you really reach a non-equilibrium steady state. Okay, so this is essentially the technique. What we do is just try to compute this potential, and from this potential study phase transitions. And so let me talk about the models. I mean, what type of models we are interested and why. I mean, imagine that we have a lattice, for instance, square lattice in d dimensions, and in each side of the lattice, I put just a stochastic variable with a Langevin equation with multiplicative noise. The same equation for each node. And then I couple the lattice just with the simplest coupling that I can do, that is just an harmonic coupling between first neighbors. I mean, this is the simplest model that we are trying to study. And the point is why we are interested in this type of models. And you see, in the absence of lattice couplings, the system is essentially decoupled. It's the same that if you have just one particle. And if you choose if you choose the drift force in this way, I mean, take the derivative of some classical potential multiplied by g squared. This is the Einstein relation. In some sense, this is fluctuation dissipation. Your system at infinite time goes to equilibrium. And you have a distribution that you can compute, and it's essentially e to the minus some equilibrium potential. This equilibrium potential is the classical potential V plus some corrections that come from the fact that you have multiplicative noise, and you see that this alpha is the prescription that you're using in order to define the Wiener process. You see that in general, this is not a Boltzmann distribution when you deal with multiplicative noise, except for alpha equal 1. You kill this, and you have essentially Boltzmann. But anyway, this is not important right now. The point is that when you couple the system, this type of coupling, that is a simple one, breaks Einstein relation. In some sense, it's breaking fluctuation dissipation, and the system is driven to a non-equilibrium system. And of course, we have no idea of which is the probability distribution in this system. So, which is, I mean, remember, what I want to study is noise-induced phase transitions. So I will choose a potential and some diffusion matrix in such a way that from the decoupled system, I have just one minimum at 0. I mean, I have a disordered system, and try to study what happens when I rise the intensity of the noise. And the simplest choice is just take an harmonic oscillator in each side, and take, for instance, a diffusion matrix. I mean, not a constant, obviously, because it should be multiplicative noise, and x squared, just because I want to keep the Ising symmetry x to minus x, essentially that. And then I have this model, this potential. I can define another parameter. I can plug in the path integral, and I can compute this path integral. Of course, I cannot compute the path integral because it's nonlinear. So what I do is just saddle point plus Gaussian fluctuations. Then you can make the Legendre transformation and finally compute the energy, the give free energy like for this non-equilibrium system. And well, this is the result. I mean, this is not a sketch for the result because, however, when you look to the result, to this result, it's quite amazing because this structure is nothing else but one loop effective potential. I mean, is quite appealing. This constant A and sigma are complicated function of the parameters, but are constant. So we have an explicit function for the potential, and we can look for phase transitions. I mean, the simplest way to look for phase transition is to compute, for instance, susceptibility in the disorder phase, just because it's simpler. I mean, put m equals 0 and compute the susceptibility, and look for the phase space in order to look where you have divergences of this susceptibility that is indicating the phase transition. So we just compute in the second derivative of this. You have the inverse of the susceptibility. We have an analytic equation that we can simply look for this phase transition. Let me show you the results. I mean, okay. I mean, we compute the critical line, just putting the inverse susceptibility equals 0. The inverse susceptibility depends on the noise. Sigma is the intensity of the noise. D is the lattice coupling. And, of course, depends also on dimensionality and that alpha parameter that is telling you which type of stochastic prescription you use it. And the result is this one. Let me show you this one first. I mean, this is the lattice coupling, and this is noise. So you see that when for weak coupling, I mean, here you have a disordered system, I mean, m equals 0, as you expect. However, when you are in strong coupling, I mean, here, for instance, near 30, you see that for very, very low values of the noise, of course, you have m equals 0, just because we build the system to do that. I mean, it's just one minimum in 0. However, when you increase the noise, you reach this faint transition and the system orders. I mean, you are getting order by rising, by increasing your noise. You are getting order from disorder. And what's happened is that when you increase even more the noise, you reach another phase transition that is, a normal one, just because the system disorders again. And, well, this is the result. The different curves are for different, essentially for different dimensions. I mean, they equal 2, 4, and 6. And you observe a very strange thing, that the critical temperature, or the critical noise, I mean, I have no temperature here, but the critical noise is somehow independent of dimensionality, some kind of universality. But this is very, very strange, because temperature, critical temperature is not universal. I mean, it's corrected by fluctuations. And for some reason, this is almost independent of dimensionality. The other phase transition that is more normal, of course, strongly depends on what type of dimensions you are. Okay, well, here is another phase diagram for d equal 2 and different values of the stochastic prescription. I mean, I can talk about this perhaps later. But the point is, well, we try to make sure if this result is correct, because remember that this is saddle point plus Gaussian fluctuations. But so we make some simulations. These are preliminary results of simulations of the system of Langevin equation. Lucas here is the responsible for that. So you see the following. For instance, this is the order parameter, and this is the noise. So you begin with m equals 0, and when you increase the noise, the magnetization growth saturates, and then for another critical noise goes again to 0. And if you compute the susceptibility, you clearly see the two peaks, and the two peaks are diverging with the size of the lattice, indicating that it's some kind of second order phase transition. Okay. Okay. So this is, I mean, this work is, I mean, we are actually doing. I put these figures right now because we finished this simulation right in this workshop. So I have. Okay, but let me try to understand why this is happening. I mean, why we are getting order by disorder, just because this is a very strange thing. And we tried to calculate in this path integral approach that is somehow easy to calculate, is entropy production in this system. I mean, in this steady state, and you can compute a configurational entropy production that is related with the stochastic path that you have in the path integral. That the definition is essentially you take the action for some path and subtract the time reverse action. I mean, you make a time reversal of the action and compute this difference. Oops. Okay. When you do that, you see that this quantity is essentially a state function. I mean, delta U means the difference of the equilibrium potential between two, an initial time and a final time. And but you have this contribution that it cannot. I mean, it's not a state function. I mean, it depends explicitly in each in the trajectory. So this is indicated that really we are out of equilibrium. Okay, but imagine that I slightly modify my model. I mean, just I change my model in this way. I mean, this is the lattice, the original lattice coupling. If I weight this coupling with G squared, that is the diffusion matrix, this type of coupling satisfies fluctuation dissipation. I mean, I can put it. I can satisfy the Einstein relation. And if we compute in this model that is slightly different from the first one, the entropy production, I see that this is a state function. I mean, this term, this strength goes to 0. So this is indicating that I am really in equilibrium. And if for this system I compute again the potential and the phase transition, we've found no phase transition at all. And the model is not so different. I mean, the difference is that one state is equilibrium and the other one is not equilibrium. So this is, well, this is telling us that in order to have this kind of phase transition, you need to have some kind of non-equilibrium stationary state. So let me summarize my conclusion. I mean, we have presented a path integral approach to compute equilibrium, non-equilibrium potentials of stationary states reached by Langevin multiplicative noise. The Gaussian fluctuation approximation, I mean, correctly captured the physics of noise-induced phase transition. I mean, we can see the transition compared with the simulations, and is all okay. And the last part that is, for me, the more interesting, it seems to be that microscopic irreversibility is a necessary condition in order to have this type of transition. Of course, I cannot demonstrate that, but this is what my model is telling me all this. So there are a lot of questions, a lot of important open problems, and one is, well, which is the cause of this noise-induced phase transition? If there is some classification of this phase transition, I mean, which is the upper critical dimension, which is the lower critical dimension, we don't know that. And of course, well, we don't know if we have a non-equilibrium renormalization group in order to classify this type of transition. So, well, this is our work, so thank you very much for your attention.